All right, how's it going, everybody? We're working on hypothesis testing, doing a practice problem for a hypothesis test of one sample proportion, one population proportion, really, I guess. It's question 38 from chapter 9 of Anderson 11E. I'm read it and then we'll work through it. A study by Consumer Reports showed that 64% of supermarket shoppers believe supermarket brands to be as good as national name brands. To investigate whether this result applies to its own product, the manufacturer of a national name brand ketchup asked a sample of shoppers whether they believed that the supermarket ketchup was as good as the name brand ketchup. So it's about generic ketchups, and what we're talking about is the proportion of shoppers, where shoppers is our population, right? So it's a proportion of the population of shoppers who think the quality of generic, where quality is just sort of broadly defined, is equal to the quality, or is greater than or equal to, right, of whatever the brand, this particular brand, right? Not brand in general, but this brand. And I'm just using mathy language here, but that's very inaccurate. I mean, just very imprecise. We just want to know if shoppers think that this brand, the generic, is just as good as this brand. That's what they care about. Okay, here I am. I'm going to use my 5-step approach. It'll hit all the points, but it's an orderly way to think about this. And we'll go as we go along. Part A: formulate the hypotheses that could be used to determine whether the percentage of supermarket shoppers who believe that the supermarket ketchup was as good as the national brand ketchup. And this right here, this whole big thing is P. We call this P. This is the percentage of shoppers who believe that. Differed from 64%. And this differed right here is not equal to, right? We want to determine if we can say that it differs from 0.64. That's what the question is asking. Now, not equal to always goes in the alternative. If we want to conclude that, that's true, that's going to go in the alternative. So what differed tells us is that we have a two-tailed test. So for step 1, which is formulate our hypotheses, it's going to look like this. Our null is going to be that it does not differ, that the true population proportion is the same as 0.64, which is what they found in the Consumer Reports study. And our alternative is going to be that it differs, that there's some difference. Now, another way to state this question is that we're just asking whether this, right, which is the sampling distribution of P bar, right, where we're drawing our sample proportions from, whether this is reasonable. Put it at 0.64, and we give it a standard deviation, which we're not going to calculate right now. But it's P, what is it? No, it's the square root of P times 1 minus P all over N. That's the standard deviation. We want to know, is this reasonable as a shape, right, as a distribution from which we pull our sample proportion? If it's not, then we're going to reject the null. If it is, then we will fail to reject it. Okay, now step 2 is to choose a level of significance. In the way that I do it. And we can look to part C for that. Right here, alpha equals 0.05. I like to do that because I think it's intellectually honest to state up front how skeptical you're going to be before you see the numbers. So, step 2 is choose a level of significance. That's done. Let me change colors a little bit. Make it a more polychromatic demonstration. Okay, so step 3 is going to be choose a test statistic. And we can already do this because we don't need anything else to do this. If we want to test this, we're going to have to know something. What we're going to have to know is we're going to have to do the same thing we've been doing, essentially. We're going to relate it to the standard normal distribution. Well, we're going to pull a P bar, and it might be this one, it might be this one, it might be this one. It might be over here, it might be over here. Whatever it is, we're going to bring it down here to Z, and then we're going to calculate the Z score, right? Because we can relate the sampling, because we know that the sampling distribution of the sample proportion is normally distributed, we can normalize it by using this score formula. So our Z, which is our score formula, x minus mu x over sigma x, in this case is going to be P bar minus mu P bar over sigma P bar, which is just P bar minus P over the square root, and that big old thing I wrote up there, p times 1 minus p over n. And that's our test statistic. So it's just z, it's just the score formula for whatever p bar we happen to get. So that's step 3, choosing a test statistic. Step 4 then is computing the collecting the data, collect data and compute the test statistic. And we can figure out what we're looking for already. It's a good idea to do that, I think. Because in order to compute the test statistic, we're going to need some things. What are we going to need? Well, we can look at our test statistic right there and see it. So we're trying to find z. We don't know what that is, right? But we're going to need p bar, we're going to need p, we're going to need n. Once we have those 3 things, we can calculate it. That's a p right there. Whoop. Okay. So let's look at the question and see if it tells us this stuff. In a sample of 100 shoppers, if a sample of 100 shoppers showed 52 stating that the supermarket brand was as good as the national brand, what is the p-value? So that should tell us all we need to know if they're expecting us to get the p-value. So we have 52 out of 100. Sample size is 100. The sample proportion is going to be 52 divided by 100, which is equal to 0.52. It's not always so clean, right? So I'd be careful about that. Make sure you do the division. So 0.52 is our sample proportion. This p bar is actually p0, right? I'll put that here too. That's the hypothesized population proportion, which is this 0.64 right here, right? What we're actually saying is, well, we pull the p bar of 0.52, and is that here or is that all the way over here, right? Which of these is 0.52? How reasonable is that? That's what we're trying to find. So 0.64 goes here, and now we have all the stuff we need to compute the test statistic. Let's make it green. So z then is going to be equal to 0.52 minus 0.64 all over the square root of 0.64 times 1 minus 0.64, which is 0.36. I can do that in my head. But if you don't feel comfortable with that, use your calculator by all means. All over 100. Okay, now I want to figure out the answer to this. So I'm going to bust open Excel, which is a very handy place to calculate this sort of thing. Equals 0.52 minus 0.64. It's going to be negative 0.012. Probably could have done that one by hand, but it's fine. Where am I? Here we go. So we have negative 0.12 on top. And what's the thing on the bottom? Well, it's going to be, I can do it all in one shot. Square root of the quantity, 0.64 times, 64 times 0.36 divided by 100. Should be 0.048. I can do it in a different way just to double check. 64 times 0.36 equals this divided by 100 equals square root of this. And 0.048 is what I get both ways. So we pop that in here. 0.048, which means that this is going to be equal to, what, 2.5, I think? Negative 2.5? Yep, negative 2.5. Okay, negative 2.5 it is. Excellent. Okay, so that's step 4 done. We've computed the test statistic. All that work, collecting all that data, which, involved a survey, which we didn't actually do, but somebody had to do, got us this test statistic of negative 2.5. And now step 5, what they want us to do is to calculate the p-value. So we'll do that on our way to coming up with a conclusion. Step 5 is evaluate the test statistic. And here it matters what kind of test we're using. It matters to calculate the p-value, we don't need our alpha yet, but we would need to know what kind of test it is. So in our little diagram I drew up here, what this says is, well, if we have z, which has a mean of 0, and it's a standard normal distribution, then 0.52 falls over here at negative 2.5. Okay, I'm going to redraw that standard normal just so we can see it when we're evaluating a little bit more closely. So This is our standard normal. 0 is here. Standard deviation of 1. We pulled a z-statistic of negative 2.5. And for a two-tailed test, our p-value is twice. This is p-value for two-tailed test. It's going to be twice the area between our test statistic and the nearest tail. Because what we're really asking is, what's the chance we would get something this extreme if we had correctly specified our true population proportion? And the chance we'd get something this extreme is going to be this times 2. So we can call this area times 2 equals p-value. So what's this area? Well, we can figure it out. The way we figure it out is we look it up on we can use a z-table, or we can use Excel. I'll do it both ways quick because I'm not sure how am I doing on time. I got 4 minutes left. Okay, so let me pull up my z-table here. Okay, so I had negative 2.5. This is a 0 to z table, so it'll tell me the area between 0 and z. It only shows positive numbers, but that's fine. 2.50 gives me a or an area of 0.4938. So what that tells me is that if I had positive 2.5, then this area right here would be 0.4938, which means because of symmetry that this is 0.4938, which means that this over here, this is going to be 0.5 minus 0.4938, which is 9, 10, 9, 4, 0.0064. So that area is 0.0064 right there. I'm going to multiply it by 2 to get my p-value, and that's equal to 0.0128. And that's my p-value. What's the chance that I would get something this extreme if I had correctly specified the proportion? 1.3% roughly is the chance. So that's my p-value right there. Whoop, circle that. Now that we're almost done, we have to decide what to do about it. So at alpha equals 0.05, what is your conclusion? That's part C. Well, if alpha is equal to 0.05, then that says that any result that's less likely than 5% means we should reject the null. That's too unlikely. There's just no way that the null is true. I mean, it's not that there's no way. It's just sufficiently unlikely we're going to disbelieve it. So p-value equals 0.0128 is less than 0.05, which equals alpha. That means that implies that we reject the null. So we believe that it is not the case that the proportion of the population that believes that generics are just as good as this brand is the same as the general result. Part D, should the national brand ketchup manufacturer be pleased with this conclusion? I think so, right? They've proven essentially that less than, right? Well, they got a number that was less. Only 52% of shoppers said that their brand was just as okay as a supermarket brand, whereas it was 64% for national name brands. So they should probably be pretty happy about that. That said, the majority of customers can't make a distinction. I mean, it's a mild majority, 52%, but majority of their sample says there's essentially no difference between their brand and the name brand. And it doesn't say who thinks it's better, who thinks which is better. In any case, if I were them, I'd probably be happy about it. But yeah, definitely would require more study. So that's how you do a hypothesis test of one population proportion. If you have any questions, post a comment or email me at jjdelaney@ualr.edu, and I'll be glad to answer. Thanks. Have a good day. Bye.